So if you haven't caught on yet, there's a bit of a theme to this session, and its challenges around associativity and commutativity, and we'll be continuing on that theme. So please take it away whenever you're ready.
It's not transmitting?
Well, I can see, well, I see your desktop. Okay.
Okay. Yeah, so it's about preprocessing your EQF. So you can just take the normal EQF implementation, you can just take your normal rule set, throw a bit of preprocessing on it, and your rules get better. So let's start with the general goal. We have some terms like a times 2 divided by 2, and we want to optimize it. And we have the general rule set, like we can distribute multiplication and division, so we can move out the y in x times y divided by z to the right. Maybe times 2 is also a shift, and times 1 can be cancelled out, and x divided by x is just 1. And if we then naively apply the rules, we can just rewrite a times 2 divided by 2 to a is shifted by 1 to the left, and then we are done. No rules applies. However, if we are a bit more careful, then we see that there is a better application rule, namely by first moving out the 2 to the right, we have 2 divided by 2, we can remove it to 1, and a times 1 is just a itself. So we see already one problem in application, which is probably familiar to all of you who have worked with EQF. We need to be careful about the rule application order. A second problem occurs when we look at, for instance, the group axioms. We have here the group axioms, it's associativity, multiplication with 1 is again the identity, and if we multiply with the inverse, then we just get 1. And now we want to prove that the double inverse of A can be simplified to A itself. But to do this, we first have to multiply with the 1, so with the identity to make the term larger. And then we have to intelligently instantiate this 1 by the inverse of A times A. And only then we can regroup to the left, have double inverse of A times inverse of A, can eventually simplify it to 1, and 1 times A can be simplified to A. So here we see another problem. We have to get creative. We have to, first of all, think about that we can multiply with 1, and then we have to instantiate this 1, and there are infinitely many instantiations. And computer scientists invented multiple ways to solve these problems. I want to focus on 3. The first one is the manual approach. Just get a few heuristics together, how you can rewrite, and apply them. It's very fast. You can do this in milli or even microseconds, but it needs an ordering. It needs good heuristics, and if you aren't careful, then you get stuck, like we have seen with this left shift example. The second one comes from automated reasoning, and it's one aspect we will focus in the next few slides on. It's Knuth-Bendix completion. You take your rule set, you complete it. We will see what completion means. And then you get a better rule set out of it with more rules, which you then can apply. It's confluent. That means you can apply it in any order, and it will produce a normal form. However, it not always works. There are some failure cases. It theoretically can apply to arbitrary rules, but sometimes it runs on forever, which is not that practical. And it's undirected in the sense that for EQFs or manual rewriting, we have a term, we want to optimize it, we apply rules to it. Knuth-Bendix completion works before we have terms. It just works on the rule set, and it combines them in an arbitrary order and produces more rules. And the third aspect, which is currently state of the art, is EQFs. We apply rules, we save all possible rule instantiations we have found so far, and then we explore basically the state space of all rules and pick the best one out of the set we have found. There are a few small problems. For instance, it's incomplete. This double inverse of A example in the group axioms, it will never find it. It will see, okay, there's no rule which applies. So maybe, depending on how you write your rules, it can multiply with 1, but that is all it can do. It will never instantiate this one if you don't say it how to instantiate it. And it tends to explode. So it tends to enumerate all possible terms, and then your computer crashes because you are out of memory. So our idea is, let's combine the two. Let's combine Knuth-Bendix completion with EGRAPHS'. The idea is Knuth-Bendix completion takes a rule set and somewhat completes it. So let's complete our rule set and then throw it to the EGRAPHS' with our extended rule set and see if it can manage to do better. So first, let's look at a short primer on Knuth-Bendix completion if you haven't seen it yet. The idea is we have three simple rules: the orient rule, deletion and deduction rule. Orient means if you have an equation s is equal to t, and we know that by some order, usually one takes the Knuth-Bendix order, but it can be more or less an arbitrary order. If s is larger than t, then we can orient it into a rule which just rewrites s to t. So we just take one orientation of the equation. Deletion says we can simplify our rule set if we have just a reflexivity rule where both sides are equal. And deduction, this is the interesting rule. We can just add new rules if s and t are a critical pair. So in the previous talk, critical pairs were already mentioned. Now we will look at an example what they are exactly. So let's take our group examples, so the three group axioms. And in the first step, our algorithm would just apply orientation and would say, okay, so in the first example, maybe orient it from right to left to move the parenthesis back to the end of the term. In the second example, x times 1, which is a larger term than x, so we will orient x times 1 from left to right, and also x times inverse of x can also be oriented from the left to the right to just simplify our terms. And now we find a critical pair. A critical pair, you can take a look here, is for instance this term, which taken the right-hand side, so the left-hand side of the oriented associativity rule, and it tried to overlap this part, x times y, with our inverse rule. So it overlaps x with x and inverse of x with y, resulting in the terms x times inverse of x times z. And on this term, both rules apply. So we can apply the associativity rule to move the parentheses to the right, or we could apply this cancellation rule to replace the left-hand side with a 1. And because we have applied correct rules to this term, we know that both resulting terms are equivalent. Therefore, we have a new rule which says x times inverse of x times z is the same as z. And then the normal orientation rule applies, orients it from left to right. And with this new rule, it continues. We again form a critical pair, again with the cancellation rule. So on the right-hand side, we instantiated z with the inverse of x. Again, both rules apply. So with the cancellation rule, with the normal cancellation rule, the right-hand side cancels out to 1. So we have x times 1, which is the same as x. On the left-hand side, and with the other rule, with our new rule, which is this one here, we know this whole term is the same as z, so it's the same as 1 times inverse of x. And if we orient this rule, you can see, okay, we are already very close to the rule we want. We have 1 times the double inverse of x is the same as x. So we have invented a new rule which we previously were missing. And then it goes on, and we'll find that 1 times something is the same as something, and eventually we find the rule inverse of x is the same as x. And now we could rewrite the example from the first-hand slide. So generally, Knuth-Bendix completion guarantees us a few things. So if our order is a reduction order, which means it's a strict partial order which is well-founded and stable under substitutions, then if Knuth-Bendix completion terminates, it produces the confluent and terminating rewrite set, which is complete on every ground term. So we can basically prove every equation we want. So we will find a normal form for every term, and we can apply our rules in any arbitrary order we want. However, there's this word if it terminates, which is a bit of a restriction because, for instance, for commutativity it won't terminate. There are extensions like unfailing Knuth-Bendix, which eventually produce every ground instantiation of rules, but generally it will run forever. So our idea is, okay, let it run a bit. It will go closer to a confluent rewrite system, and we hope that our partial system in between is confluent enough and has good enough rules. We will make this good enough a bit more precise in the evaluation section. So I mentioned there are a few opportunities. Namely, we can find two new kinds of rules. The first one are shortcut rules. So in the example where we have some a times b divided by b, we can apply our rule which moves the b to the right, then we have a times b divided by b, and then we can use this rule b divided by b is 1, and then we can use times 1 is the same as just the left thing. So we can apply 3 rules, but with Knuth-Bendix completion we will get a rule which expresses all these 3 rules in one rule, which just says a times b divided by b is a. So there are a few shortcut rules which might help to bridge the explosion gap of EQRAPHS, because it will in shorter time find better terms. It will directly skip a few rule applications if the term matches, and therefore it won't pollute the memory of our computer so much. And more interesting, on the right hand side, we have new rules, like this double inverse rule with the group axioms, which were previously not present in our EQRAPHS. So we have truly more power than our original rule set had in the EQRAPHS. Given that, let's look how we do it. So we have a relatively simple algorithm. First of all, so we first run Knuth-Bendix completion. Here it's step 2. I will talk about step 1 shortly. So we run Knuth-Bendix completion using the tree equational theorem prover to obtain a few critical pairs and the resulting rules. And until we have obtained n rules, so if we have obtained then n rules, n could be 100. So after obtaining 100 rules, we orient on our rules. And there we tried different modes. For instance, we could say, okay, take all new rules and only the new rules and then go with it. Or take the new rules and re-add the original rules we have from the EQRAPHS back in our rule set. This is important because, for instance, some rules like x times 1 is the same as x are sometimes applied in both directions in EQRAPHS. So we not only want to simplify x times 1 to x, but also sometimes we want to multiply with the 1 to have x goes to x times 1, and then maybe more rules apply and can simplify it. So sometimes you might want to keep our original rules even if they are oriented against the intuition. And then we just run the EQRAPHS algorithm on our new rule set. And we also tried a greedy algorithm where we just apply the first rule that matches. And in the sense that if our rewrite system is somewhat confluent, then it shouldn't matter in which order we apply the rules. And then I have also this first step, which is filter, because I mentioned there's a problem with commutativity where we can't orient commutativity, and therefore we can only work on concrete instantiations which we can orient. So we also tried, okay, if these rules make a problem, just take them out. So to the interesting part, what does the runtime say? So on the left hand side, we have a log scale block for time. So we tested at 10,000ths of a second, thousandths of a second, up to a second of time, with different rule sets. So in blue, you see the base rule set, which starts in 10,000ths of a second, roughly at 10 symbols, which are simplified. So we get a large term. We apply the rule set, and turns out the EQRAPHS can cut out on average 10 symbols. And if we give it more time, it goes up to, and eventually it can go up to 13 symbols can be cut out of the term with the normal EQRAPHS rule set. And then we have a few comparisons. For instance, with Knuth-Bendix completion, if we just take the Knuth-Bendix completed rule set, we see if we have basically no time at all, we are a bit worse. But as soon as we get 1,000th of a second, or yeah, this should be roughly 1,000th of a second, then we are a lot better than the EQRAPHS, so we, in the same time of a thousandth of a second, we managed as much as the EQRAPHS managed in 10 times the amount of time. And eventually we managed up to 14 symbols reduction. And yeah, we also tested out this no unorientable rule set, so we cut out this commutativity rules. And it turns out, if you have enough time, it's worse. It doesn't manage to prove as much as the extended or KBC rule set. But if you have no time, so if we basically just run a few instantiations of a rule and then extract the best term before the EQRAPHS has time to explore really, then these no unorientable rules are a lot better than basically all other rule sets, probably because they are more confluent. The rule set could go more in the confluent direction because they didn't have these unorientable rules, and therefore it managed to optimize more. Then on the right-hand side, we have the idea followed through. So let's say if our rule set is somewhat confluent, just apply it greedily. And it turns out if we have no rules, it's quite bad, so around 7 rule symbols. And if we then go larger, we see, okay, it simplifies more and more if we have more rules, up to 2,500 rules, where it reaches roughly 11 symbols of reduction. And the best is with the extended rule set in this case. And if we remove the unorientable, then we are in the lower two cases. So it needs greedy needs unorientable rules. We manage it, so we make sure that we only apply once to not run an endless loop, but they seem to help together with some other rules. But overall, we see the greedy rule set can't simplify as much as our original rule set. So we are 11, and 11 is roughly in the middle of the left graph. So greedy is still a lot worse, even though our rules make it better than before. Okay, this slide. Sorry for there's a small problem with the slide set. Okay, and if we look at the rule set number in the EQRAPHS setting, we have this picture. So we see that if we have basically no rules, we have the same curve from before. We've managed around 10 symbols in no time, and eventually we manage up to maybe 13 symbol reduction. And if we add more rules, it gets better. Except if we go above 100, then we are in the yellow and gray lines, which means if we have less time, more rules doesn't really bring anything because they pollute the memory and pollute the space. Therefore, we don't manage to explore so much. We stay basically in the same term set, and therefore we can't find the good terms. Only if we then have enough time, we again find good terms. So we found that around 100 rules is the sweet spot for our completion. In our ongoing work, we look at conditionals. So there's also a few sections in the extended abstract, which is on the web page, where we looked at what can we do with, for instance, division, where we want to make sure not to divide by 0. And then one has to be a bit careful because Knuth-Bendix completion usually doesn't have conditionals. One could split it, or one could add if rules, and we explain it in the paper. Another is how to reorient these rules. For instance, another option we are currently looking at is just make all rules bidirectional where it's possible. So we find rules by Knuth-Bendix which are oriented, but maybe the other orientation is more helpful to explore more rules. But our preliminary results say it just explores the EQRAPHS faster. And another very interesting direction is to move the Knuth-Bendix completion into the process during the EQRAPHS. So while rewriting in the EQRAPHS, maybe just use critical pairs between the rules we really use and skip all the unnecessary rules which Knuth-Bendix would otherwise explore. So to conclude, just pre-process your rules with Knuth-Bendix completion. It finds better results faster, so it finds the same result in faster time, and it sometimes even finds more results because it adds novel rules. And even with Knuth-Bendix completion, greedy stays worse than EGRAPHS'. And in the future, we want to look at a bit more how can we select the critical pair rules. Currently, we just use the ones that tree spits out in the order tree spits them out, but there might be some gems in there and a lot of garbage, so we want to be a bit more selective. Okay, thank you for your attention. I'm happy to take questions.
Thank you. Yeah, we definitely have some time for questions.
Can we look at the first slide, very first slide?
Yeah. Okay. Then.
Yeah. So I want to see the both example. Yeah. So Knuth-Bendix completion is well motivated if you are writing a single term instead of term bank, because if there is no non-confluence, if there's a critical pair and you take one path, then you lose access to the other part. But it seems to me that this motivation doesn't really apply to EGRAPH. So for example, for the example on the left, EGRAPH have no problem just doing this derivation because it is not throwing like one half of the critical pair away. And for the example on the right, so you write x times 1 equals to x, and usually when people apply EqSat, they will put both direction of the equation as a rewrite set to do EqSat. So EGRAPH has no problem deriving the example on the right as well. So I think like I would need some more motivation to make it convincing to me that Knuth-Bendix completion actually is beneficial for EGRAPH. So this is my first question. And the second question is, yeah, of course, due to your evaluation, you see there's some improvement, but I have a null hypothesis. So if you do Knuth-Bendix completion between two rows L and R, you are kind of inverting one row like L and composing it with R. So doing Knuth-Bendix completion to resolve a critical pair L and R is sort of like adding a row inverted L compose R to your rewrite system. So I have a null hypothesis that all the improvement you are observing are just effect of rule composition. So you are making some rule that effectively do multiple rewrites in the original rule set. So I think like to reject or prove the null hypothesis, I will want to see like what happens if you just do ordinary rule composition and see and see if that preprocessing already enhances your rewrite set. So that means like you have a bunch of rules and you just sequentially composing them and add them to the rewrite set. And does this provide improvement? How does this compare to Knuth-Bendix completion?
Okay, thank you for the question. First, to the first part of your first question. So yes, in the sense, so it was about EGRAPH explores both paths. In that I agree, because the left-hand example, it's solved by an EGRAPH, and so there it was more about maybe we can with Knuth-Bendix completion just skip EGRAPHS and do greedy rewrite, which the eval turned out wasn't the case. And so now onto your second question, it was about shortcuts, and if basically all we find are shortcuts, all rules. And yeah, so one could postulate these shortcuts don't really help much. I can't prove or disprove if these shortcut rules, which are implied by other rules, help or not. One would need more experience. But I at least can say for the second example, an EGRAPH is never able to optimize this term. So if we add both directions, so we can add both directions for the first and for the second rule. For the second rule, it would basically, because it says x goes to x times 1, it would grow over EGRAPH quite fast, because every node in every E class would have a times 1. So, well, it goes at least a bit. But we would find this rewrite from going A inverse to A inverse times 1. But we can't add this rule, x times inverse of x to 1 in the other direction. Because in the other direction, we would need to instantiate x with arbitrary stuff. So we could add it for the concrete instance, a times inverse of a goes to 1, or b times inverse of b goes to 1, or inverse of a times inverse of a goes to 1, or in the other direction. So we could add concrete instances, but generally we would need all of these instances to rewrite some double inverse. So if we have a more complex term with a double inverse, we would need this complex term inside the rule instantiation, which would blow up, well, basically it's the whole Herpra universe in our rule set. I hope this answers the question.
So I think now I get it. So
I think we should maybe take the rest of this question offline.
Okay.
We do have time for maybe one more quick question, if anyone has any.
Hello, I have a short question. I assume there should be an order for KBC to work on your row set. Maybe that's already in your talk and I missed it, but could you explain, like, is there is it row set by row set, or you have a common method to determine such a order you're going to use?
Yeah, so it was about the question about the rules, about the order in Knuth-Bendix. And the order needs to be a reduction order, that is, it's a strict partial order, which is stable under substitution. So whatever we substitute in our rule, it has to the order has to be preserved, and it has to be well-founded. So then for that, every order which fulfills it works, and one common order is the Knuth-Bendix order, which just says, which is basically or very similar to a lexicographic path order, where we go through the term, we have a precedence on our function symbols, which can be arbitrary, but one could also say, for instance, multiplication is more expensive than addition. And so this order, so this Knuth-Bendix order can be, for every signature, it can be derived, and it works always.
Okay, and with that, let's thank our speaker one more time.